Hello everyone, let me introduce myself. My name is Encalada. I am Mechatronics engineer graduated at SPOL, and today with my research partners Christian, Brian and Yolanda, I am going to present you our work titled Wind Turbine Multi-Fault Detection based on SCADA data via an AutoEncoder. The outline we are going to review in this presentation is composed by 5 parts. First one is introduction, second one is the data description, next we have multi-fault detection model, next we have results and discussion, and last we have conclusions and the further work. Okay, introduction. As we know, to produce a lower environmental impact, there is a strong attraction towards renewable energy. Wind turbine is one of those alternatives with a huge acceptance around the world. The growth of installation of wind turbine farms is more frequent along last years. When we talk about large projects like this, it's unavailable refers to operations and maintenance costs. This can overcome approximately the 20% of the total energy generation cost. When wind turbine has a lot of downtime, its productivity decreases and the operation and maintenance costs increase. In contrast to that, condition monitoring systems appear as a suitable strategy since condition monitoring is applicable, even when in an offshore environment where conditions could be worse and terrible, as we know. That's why early fault detection has become a meaningful strategy to increase the competitiveness and productivity of wind turbines. On the other hand, we must introduce the concept of SCADA. Supervisory control and data acquisition systems are installed in all industrial science wind turbines. Most of the fault detection prognosis strategies use data of vibrations, for example, sounds, etc., which requires additional sensors installation. That's why we propose a methodology where we use only SCADA data to detect faults in wind turbines. These are the main features of the simulated wind turbine by FAST software, which is a product of National Renewable Energy Laboratory located at USA. In this table, we can see that characteristics like rated power, number of blades, hub height, etc. Belonging to the wind turbine. In this another table, we have instead the installed sensors into the simulated wind turbine, like generated electrical power, rotor speed, generator torque, etc. As we see, we have also added a little bit of noise power in order to do the simulation more realistic. Originally, 8 faults were performed in all simulations done on the wind turbine. However, for this work, we have just selected 3 of them, which are related to pitch actuator, generator speed, and torque actuator. As of the performed simulations using FAST software, we collected data in what about we are talking about now. 260 simulations were done, and these are divided into groups. 100 simulations with healthy data and 160 simulations with faulty data. These 160 ones, 20 simulations correspond to each fault. Recall I said that originally 8 faults were taken into account. Each simulation has a temporal window of 600 seconds, as of which the first 200 seconds correspond to a transient state. That's the data we don't use, while the last 400 seconds correspond to a steady state. That's the data we use instead. Recall also that the data were down sampled to a period of 1 second, with which we set the frequency like this is a SCADA system. With respect to data split, we must take into account that this is a normality model, that the algorithm is trained with only healthy data. The algorithm, which is an autoencoder, will be explained with more detail later. So, for the data split, we use 70% of healthy data for train, 20% for validation, and the last 10% for test. In this way, we complete the 100%. As we see also, the 100% of faulty data is for test, since in the test we enter both healthy data and faulty data. When we have data with different origin, magnitude order, etc., we must employ a standardization strategy in order to put all data on the same scale and don't add a certain bias to certain features. In this work, we use min-max scaler, which scales the data in a range from 0 to 1. To do this, we compute the minimum and maximum values for each column, and then we compute the scale values as we see in the equation. In order to work with the aforementioned described faults, we need to establish the next concepts: sampling time and detection time. Detection time is the elapsed time between the fault occurrence and its detection. It's related to sampling time because we have the detection time in terms of the sampling time, as we show in this slide. For example, for fault 1, we see that this requires fulfilling that detection time is less 100 times sampling time. The number of times we also call J, or the number of sampling periods. In this work, to be more restrict, we selected two shorted numbers of sampling periods, which are in this case 3 and 10. In this slide, instead, we show the matrix transformation since originally we have a matrix with 400 columns, which represent the 400 seconds of simulation, and this matrix has 260 rows, which are the number of simulations instead. Now, considering the J value, we reshape that matrix into another matrix with J columns and many rows. So, next we have the multi-fault detection model. In this figure, we can see the application of the above matrix transformation, because that's the data reshape done for each sensor. As we can see, in this case, we observe, for example, 3 columns per sensor, which is J value equals to 3. Next, with the prepared data, we are ready to send those to the AutoEncoder for the training stage. In this figure, we see that the predictions of this model, which are the reconstruction basically of the input, that an AutoEncoder works. Between the input and output, there is a reconstruction error as of which we said if there is a low error, probably the sample is healthy, but if the error is large, for example, probably the sample is faulty. Recall that the model was trained with only healthy data. As of the computer errors, these are displayed as a matrix. Then we have to transform these to a representative error per row or tested sample. Before continuing with the explanation, this table remains the architectures of the autoencoders for each J value. For example, we see that the numbers of neurons change and the other hyperparameters remains static. So, going back to the slide 18, we compute those errors using the root mean square error applied to each row or tested sample. G is the total number of columns since we have 9 sensors and 2 possible values for J. These are 3 and 10, as we said. Observing the data, we see and know that several variables make data take a sinusoidal behavior, so we cannot clearly see the trend of the data. And then it could be kind of difficult to detect a fault. Moving average appears instead as a strategy to extract the trend of a time series, computing the mean of shorter and successive time series. The presented equation in this slide computes those time series mean or average, in which we must define the temporal window or the lag. For this case, we set 30 minutes as the lag. Now, in order to detect the faults over the healthy region, we propose a metrics based on the statistics of the training errors. For example, we take the mean and add 3 times the standard deviation, so we set a threshold which defines clearly 2 regions where a sample can fall. a healthy case and a faulty case. Now we see the results and discussion finally. For example, in this figure we present the results, and as we can see, we have two dashed lines which define into this figure the healthy zone. For example, we observe that black samples are detected as healthy, and that's correct. In the other hand, we see that, for example, there are three well differentiated curves which are located on the healthy zone. So these have been detected as faulty, and that's correct also. Eventually, we conclude that all samples in two scenarios, G equals to 3 and J equals to 10, were correctly detected as faulty or healthy. As of this, we can take some conclusions and we define the further work. We have some ideas. For example, with J value of 3, the prediction errors are lower, attaining a better performance with a shorter detection time. That's important. And the combination of an autoencoder with as a normality model shows being a great strategy to make multi-fault detection. The downsampling strategy is useful also in order to feed the data as if a SCADA system has generated them. It would be interesting to include data augmentation, for example, techniques in order to apply other deep learning strategies, for example, CNNs, RNNs, etc. And with that, we conclude this presentation. Thank you so much. Does anyone has any question?